So the last couple days we've been talking about ionic compounds and molecular compounds, but mostly within the context of how to name them or how to write their formula. And we're still going to do a little bit of that here and there over the next few days, but I'm not going to do any more teaching to do that. We'll just spend some time kind of practicing here and there. Important skill though, because if we can't write the names and formulas for ionic and molecular compounds, writing and balancing full chemical reactions will be impossible. So if it is something that you are struggling with, please make sure you come in and see me in scheduled helper at lunch, okay? And we can get that straightened out pretty quickly, all right? But take advantage of the fact that I'm here to help you, okay? If you're struggling with the naming stuff, we can work it out. Okay, so today we're going to talk about the properties of ionic and molecular compounds. And what I mean by properties, like their characteristics. If I look at them, what do I see? Okay, things like that. This is going to be important information for the lab that we're going to do next week. Next week, you will get in the lab about a dozen unknown compounds. They'll just be labeled A through like J or A through K, whatever the 12th letters, something like that. Okay, so they'll be labeled just with letters. I will give you a list of the identities. You will have to figure out, is A water, is B salt, is C sugar, okay, that kind of stuff. Okay, and you'll have to do that using just their physical properties. All right, so we're going to look at what are some of the physical properties of ionic compounds, molecular compounds, and things like that, and that'll allow us to be able to do the identification process on Thursday of next week. Okay, everybody kind of with me there? All right. So we're going to look at the properties of compounds, acids, bases, ionic, molecular things. Okay, understand how these properties can be used to identify a compound, and like we said, that's going to be useful when we start designing our lab next week. Okay, there's two kinds of properties. There's chemical properties and there's physical properties. Okay, physical properties are things that are observable with just that particular material. A chemical compound is not, a chemical property, is not readily apparent until that material reacts with something else. Okay, so chemical properties are things that are only going to be discovered through a chemical change or chemical reaction. Okay, so just by looking at gasoline, okay, can I tell that gasoline would explode if it was ignited? No, I can't tell it just by looking at it. Sure, gasoline smells funny, and we associate that smell with gasoline, which we know is flammable. But if I had no previous experience with gasoline, I would say that's a pretty funny smelling liquid. Okay, there would be no indication that that stuff could be harmful, okay, or explosive, or flammable, or whatever. Okay, just looking at it doesn't tell me that. Okay? Its ability to ignite and burn is a chemical property. Everyone follow me there? All right. So some of the physical properties that we're going to be looking at are things like color, okay, density can be a physical property, melting point is a physical property, solubility is a physical property, okay, things of that nature. So there's lots of different physical properties that we will be examining for these unknown compounds. All right, things about ionic compounds, and we talked about this briefly the other day, but ionic compounds typically exist as crystalline solids or salts at room temperature. They have very high melting points, several hundred degrees usually. Okay, so if I look at something, an unknown compound, and it's a crystalline solid, is there a good chance it's ionic? Is it 100% for sure? No. Okay, there are molecular compounds that are crystalline solids. Sugar is a molecular compound that's a crystalline solid. However, sugar, because it's molecular, will show some other properties that are indicative of molecular compounds and not ionic. Okay, things like it has a very low melting point compared to salt. Okay, things like that. Easy question. Exactly. If I dissolve it in water, it won't conduct electricity because it doesn't split into charged particles. Only ionic compounds do that. Okay. So ionic compounds is our second thing here. Okay. Will also conduct electricity when they are in solution. In fact, that is a defining characteristic of an ionic compound. That is something that all ionic compounds will do that molecular compounds will not. All right. In fact, that would be the only way in next week's lab that you would be able to tell sodium chloride from sucrose. Okay, that's salt from sugar. Right? That's the only thing that would tell them apart. because you're not allowed to do a taste test. Because there are other white crystalline solids that are in there that could be bad for you. Okay, so no taste tests. Okay, that's out for ways to identify things in the lab next week. Okay. All right. Now that's again because when we put something in water, okay, so if I put a chunk of, of salt in water, okay, the salt will dissociate. That is, it'll break up into negatively charged chlorine atoms. That's the green atom there, okay, surrounded by water, okay, and it'll break up into positively charged sodium ions, okay, again surrounded by water molecules there as well. All right, so it'll slowly dissolve, and that's what will produce this solution that will conduct electricity. So if I have pure distilled water, will it conduct electricity? No. Okay, pure distilled water will not, because it doesn't break up into positively charged ions and negatively charged ions. Will tap water conduct electricity? Yeah, it will. Okay, it's got all kinds of ions in it, right? We get it, it goes through the treatment plant, they add chlorine to it, things like that to kill bacteria, right? It's full of calcium, okay? Calcium is that stuff that you see building up on the inside of your shower, okay? Things like that. Those are all ions, they're in tap water. Tap water will conduct electricity very well. So next week when we do our lab, when we're testing the conductivity of a solution, should we be using distilled water or tap water? Yeah, we better use distilled water. And if we use tap water, everything will conduct electricity because tap water conducts electricity. You guys follow me there? I don't want to make a solution of tap water and sugar. It'll conduct electricity. That's not what I'm looking for. I have to use distilled water so that if I put an ionic compound in it, then it will conduct. If it's not an ionic compound, it still won't. All right, so I have to use distilled water when I'm running a solubility test. Okay, so big things here. Ionic compounds are crystalline solids. Okay, all of them are. Doesn't mean every crystalline solid is ionic, but all ionic compounds are crystalline solids. Okay, and they conduct electricity when they are in solution. Okay, so two important characteristics or physical properties of ionic compounds. Now, if I was able to, have a microscope and something like, and looking at the crystalline structure of every ionic compound is slightly different. Okay, their crystals will have a different shape depending on what they are. That's not something we're going to look at because it takes too long, and then we'd have to have a chart of, okay, well, this crystalline shape means this one and whatever. So we won't do it that way. Okay, there are several ionic compounds, that is, there are several metals that when they are in an ionic compound will produce brightly colored salts and thus solutions. Right? So if I have something containing copper, I will get a blue solution and more than likely a blue salt. Okay, it'll probably be a blue crystalline solid if it contains copper. And when I dissolve it in water, the solution will also be blue. Okay, nickel containing compounds will be green. In fact, I'm just going to change what I did here. Okay, so copper containing compounds will be blue. Okay, nickel containing compounds will be green. Okay, it'll be a green salt. Okay. And cobalt containing compounds will produce pink solutions. I don't have pink, but I'll use red. Okay. And in fact, many of the cobalt salts are actually reddish in color. They're kind of pink in solution, but the salts themselves can be like blood red sometimes. Okay. So if I have a red crystalline solid as my unknown compound, okay, I put it in water and it dissolves. The solution conducts electricity. And is it a pretty good bet that it's something that contains cobalt? Yeah. So if I was looking at my list and I had something on there that was like cobalt nitrate, that would be it. Okay, that would be the only red crystalline solid that would conduct electricity on my list. Right. Similarly, if I was looking at a blue crystalline solid that dissolved easily in water and the solution conducted electricity, okay, that would probably be something that contained copper. Right. And so I would just look on my list and go, oh, well, there's the only copper containing compound. I'm going to say that sample J is copper chloride or whatever it happens to be. All right. Kind of following how we're going to run this process next week. All right, so those ones will be important. Okay, there are a couple of other ionic things that can happen, and you'll probably want to write these down. Okay, compounds containing ammonium. Okay, that's that complex ion or polyatomic ion that has the positive one charge, acts like a metal. Typically, ammonium containing compounds will get colder when they dissolve in water. Okay? Okay? In fact, this stuff, what would the name of that be? I have somebody other than Ethan give it to me this time because I know you know the answer. What's the NH4 stand for, Andrew? Ammonium, what's the NO3? Who's got their periodic table? I can check it. You should have your periodic table out. That's my subtle way of saying that. Nitrates. Okay, so this is ammonium nitrate, NH4NO3. Anybody ever use one of those commercial cold packs where you pop the little water bladder and then shake it up and it gets cold? Okay, the stuff that's inside there, the crystalline stuff, is ammonium nitrate. Okay, the little bladder that's inside that you pop just contains water. When that stuff dissolves in the water, it gets cold. Okay, there's enough of it in there that it dissolves over, it stays cold for 15 or 20 minutes, which is as long as you're supposed to ice an injury anyway. Okay, so it's good for that. Okay, and it doesn't require us to have refrigeration. It just gets cold. Okay, because that's what it does when it's in solution. All right, so that would be one, just in case that might be one of your unknown compounds. Next week, hint, hint. All right. Now, molecular compounds. Molecular compounds can be solids, liquids, or gases at room temperature. Okay, they could be crystalline solids. They can really be anything because they have lower melting points. Okay, something like butter, for example, is a molecular compound. It's a low melting point. You put it in your hand, it'll melt. Okay, same with coconut oil. Okay, something like that. So they can be solids, liquids, or gases at room temperature. So if I give you an unknown compound next week and it's a liquid, it's definitely not ionic, okay, which would eliminate more than half of the unknowns from your list. All right, as soon as you see that it's a liquid, you know right away this is not an ionic compound, and you've already narrowed it down to a bunch of your molecular ones. Okay, and then if some of your molecular ones are sugar and things like that you know are solids, well, you're probably only going to be left with like 2 options, okay, on your list. So knowing that they can be solid, liquids, or gases is important. There will be no gases in the lab. They're very hard to contain and give you a sample of. Okay, put them on a little dish because they just float away. Okay, yeah, so they're kind of tough to use that way. All right, so molecular compounds, like we say, can be solids, liquids, or gases at room temperature. Okay, they have low melting and boiling points. Okay, molecular compounds are not usually as soluble. Okay, not good to have rules that contain usually because then it's sometimes, and we don't like that. Okay, but they're not usually as soluble as ionic compounds, and they do not ever, conduct electricity when they're in solution because they don't break up into charged particles. Okay, is it possible for one liquid to be soluble in another? Yes. Absolutely. Okay. It's also possible for one liquid to not be soluble in another. If I pour oil into water, they separate. Okay, oil's not soluble in water. But if I pour alcohol into water, okay, will that dissolve? Yeah. Okay, alcohol is soluble in water. Oh, that's a big bug. He's a little flatter now. Okay, so we've got that, yes, liquids can be soluble in other liquids. If that's the case, how will I know? Like if I pour a liquid into another liquid, how will I know if it's dissolved in, especially if they're both clear? Okay, well, it probably won't, right? Because they'd both be molecular compounds. One would be distilled water and the other would be something else, like let's say alcohol, okay? But all I need to look for is any evidence that it isn't soluble, right? If they are soluble, then they'll just become one part. Okay, if they are not soluble, then there will always be a small line between the two. Even if they're both clear, you'll be able to see where one sits on top of the other. Okay, now that can happen sometimes with things that are soluble. Sometimes you just have to stir them. Okay, you give them a little stir, then they don't separate again after that. Okay, everyone all right with that idea? Okay, so just something to watch for. Okay, the other thing about molecular compounds is there are very few that will produce brightly colored solutions. Okay, when they do dissolve in each other, they basically just assume whatever color they were before. It's usually dull or muted, okay, or just clear. For example, again, putting alcohol in water, okay, if it's just clear, like rubbing alcohol, you just get a clear solution. Right. Okay, if I put sugar in water, do I get a clear solution? Yeah. Okay, so again, molecular compound dissolved in water. Okay, it's not producing anything brightly colored. All right, acids and bases. There's two kinds of acids and two kinds of bases, strong and weak. Okay, strong acids. Okay, strong acids always contain hydrogen acting as a metal. Okay, so they'll be like hydrogen chloride, hydrogen sulfide, okay, hydrogen bromide, whatever. It'll always be hydrogen first acting as a metal. Okay. That means that they are all what kind of compounds? All the strong acids. Ionic, because hydrogen is there acting as a metal. Okay, if it has a metal in it, it's an ionic compound. So our strong acids will be ionic compounds. Okay. That contain H+. All right. So presence of H+ in a solution gives it acidic properties. Acids are ionic compounds, thus share many of their properties. That is, again, strong acids. Weak acids are molecular compounds, usually. Okay, for example, citric acid. Okay, the stuff that's in all citrus fruit is a weak acid. Has a pH of like 4.5, 5, okay, somewhere in there. Okay? It's acidic enough that it's kind of tart, okay, but not like burn your face off, okay, kind of acidic. Right? Whereas our strong acids, they are going to be very, very strong, okay, and they're going to have lots of H+ in them. Okay, does that mean there aren't weak ionic acids? There might be a couple, but for the most part, ionic compounds are going to be, if they contain hydrogen, are going to be strong acids. Now, some examples would be hydrochloric acid. This is the stuff that's in stomach acid. Okay? You have it in your stomach right now. It helps to break down proteins that you eat, okay, and digest your food for you. Has a pH of about 2. Okay, how does it keep from eating your stomach? Yeah, it's got a lining, mucus actually. Your stomach is lined with snot, okay? And the snot is a protective layer that's constantly being rejuvenated, okay, to keep the acid from burning your stomach. If something happens to that lining, the acid will burn your stomach and you get an, starts with U, an ulcer, exactly, okay? You get an ulcer if the stomach acid actually burns the inside of your stomach. It's a chemical burn that can even lead to bleeding, okay, if they get really serious. It's a pretty serious health problem, okay? But there is really strong acid in your stomach. Okay, another strong acid would be like hydrogen bromide. Okay, and then we could have things like H2S. Okay, or we could have H2SO4. Okay, we could even have this. Which one do you think is the strongest? H3N. The more hydrogen ions that compound will break into when it hits the water, the more acidic it will be. Okay, so the stronger acids are the ones that can put more H+ into a solution. Okay, nitric acid is in fact so dangerous that even the fumes from it, okay, can cause severe chemical burns on the skin. So can hydrogen chloride. Okay, I had one time when I was, I think it was my second year of teaching, I was mixing some hydrogen chloride for a lab, and I sneezed right over top of the container. And then right afterwards, you sharply inhale, and I inhaled the fumes of hydrochloric acid, knocked me unconscious flat on my back. One of my colleagues came in and saw me laying there on the floor, blood streaming, thought I was dead. Okay. Yeah, it was pretty gross. Okay. But this stuff is pretty harmful. I inhaled it and went into my sinus passages and actually caused them to bleed a little bit. Okay. So yeah, you got to stay away from that stuff. Nitric acid's even worse. Okay, when I was in high school, we were doing a lab with this stuff, and a couple of people had forgotten to put the lid back on their container of it, and they were doing stuff with their hands over top of the container. Okay, a few hours later, they were wrapped up in bandages because they had chemical burns all over their hands. Okay, just from the fumes from that stuff. So it can be really strong and really harmful. Yep. Yes. Yeah. Oh, absolutely. H2S is one of those harmful gases that is associated with natural gas and oil reserves and things like that, which is why you have to get your H2S certification if you become an oil field worker, okay? Because you have to know what the proper procedures are when you encounter it. Because yeah, the inhalation of hydrogen sulfide is incredibly bad for your lungs. It'll kill you pretty quickly. Okay? So they ask you always to stay inside if there's a known leak of that stuff. Okay, so strong acids are going to obviously have a very low pH. Okay, that is, they will have a pH of less than 7. That's one of the things we're going to test in the lab. Okay, we'll have the litmus paper that changes to different colors. All right, 1 through 14. Okay, what you'll do is dip it in the solution and then compare it to the color chart. Okay, and find out what the pH of the particular unknown compound is. So if you get something that's 1, okay, it's going to be an ionic compound that contains hydrogen. All you got to do is look on your list and find out which one. Okay, and then obviously we have here acids taste sour or tart and will turn litmus indicator acidic colors. Again, we're not doing any taste tests, okay? Because some of the acids that you will have in that will taste tart and it'll be the last thing you taste because it'll burn your tongue off, okay? So no taste tests in this, all right? I would say it would also be wise to not like aggressively sniff anything in there. How do you like get an odor test for something that's unknown? Starts with W. Wafting. Okay, so you do this. You put the sample about arm's length away, and you waft the smell to your nose. Okay, you don't go over top and go. Okay, because that'll not go well. Then you'll end up like me, flat on your back, bleeding from the nose, unconscious. Okay, don't want that. All right. So those are going to be the properties of acids. Okay, if we get a strong acid, it's going to be an ionic compound containing hydrogen, which means that its solution will also do what? All ionic compounds, their solutions conduct electricity. Okay, so we got to be ready for that as well. Okay, bases. Strong bases are also going to be ionic compounds. Weak bases can be molecular, but strong bases are going to be ionic compounds. Okay, and they are going to contain hydroxide, OH. Okay, they will obviously have a pH that is higher than 7. Okay, their solutions will conduct electricity. All right, so if I have an ionic compound its solution conducts electricity, okay, and then it has a pH of like 14, right? Then I'm looking for any compound containing hydroxide that is ionic. So let's say I had these two choices. Which one of those would have a pH of 14? Yeah, the sodium hydroxide, because the other one is alcohol. Okay, it's molecular. Okay, C2H5OH is ethanol. Right, same stuff that's in like rubbing alcohol or drinking alcohol. It's that stuff. Okay, that would not have a pH of 14, or we wouldn't use it for those purposes. Okay, it has a pH actually of about like between like 6 and 7. It's just slightly acidic actually. Okay, so it's not a base at all. Okay, it just happens to have OH in it. It's not OH like this. It's actually an O and an H in a group together on the molecule. Acts completely different. Okay. All right, so things like that are things we're going to have to think about when we're trying to identify our unknown compounds. Okay. All right, we talked yesterday about designing our lab, okay, or sorry, about what our lab reports are going to look like. So for our procedure for next week, and you're going to want to write this down because it's not in your notes, you're going to have a few tests that you're going to want to run on your unknown compounds. Okay, those tests will be you will want to run an observable properties test. Okay, this is probably the simplest one, but it will have the most things for you to record. Okay, observable properties are things like color, odor, um, state, okay, nature, and by nature I mean like is it crystalline, okay, or waxy, okay, or something like that. Okay, the nature of its appearance. Okay, so color, odor, state, nature, okay, anything else, okay, that you think is important, okay, that you can observe just by looking at it. Okay, that would be your observable properties test. Okay, another difference we said between, in general, ionic compounds and molecular compounds was their solubility. Okay, we said that ionic compounds are generally quite soluble, whereas molecular compounds tend to be less so. All right, so I would say a good test to run next would be a solubility test. Okay, during a solubility test, obviously you want to look for evidence of the material dissolving. Okay, that would be if the liquid assumes the color of the crystals. Okay, so if they have blue crystals and the solution becomes blue, obviously some of it's dissolving. Okay, if the crystals appear to shrink, okay, so any changes in the material. Okay, and by that I mean like does it shrink, okay, or something like that. Okay, and then we also want to watch for any changes in temperature. Changes in temperature can indicate several things. Okay. A change in temperature, and this would be an increase in temperature, is usually indicating the presence of a strong acid or a strong base. Okay? When you add water to a strong acid or a strong base, it generally gets hot. Okay? And you would notice that even with a very small amount of sample, you would notice a change in temperature. Okay? It'll be sharp and immediate. Okay? In fact, because of that, anytime you are mixing or diluting an acid, you always add the acid to water, not the other way around. Okay, you never add water to acid because acids don't retain, they don't absorb energy as well as water does. Water can absorb that heat and not get as hot, and it doesn't work the other way around. If you're putting a small amount of water in a large amount of acid, it'll get so hot that it can break the container. Okay, going the other way, water, if you add acid to water, you're adding a small amount of acid to a large amount of water, the temperature doesn't change as much. Okay, so it's always safer to go that way. Okay, add water to the material, or sorry, add the material to the water, not the other way around. Okay, so if there's an increase in temperature, that can indicate a strong acid or a strong base. A decrease in temperature can indicate the presence of NH4. All right, so at this point, I'll have now kind of recorded anything that was readily observable. I will have now put the material in water. What could I logically test next that will tell me something really important? Okay, I might try the smell now, but I should probably test it along with the observable parts, because sometimes when I put it in solution, yeah, there might be a new smell, so it's always good to check, but that might be the result of a reaction, okay, which is still going to be an important observation to make, but we also want to know what does the thing smell like before I do anything to it. So probably check that twice, yeah. Yeah, exactly. We want to run a conductivity test next, because that conductivity test will tell me 100%, okay, whether it's ionic or molecular. Okay, so that conductivity test will tell me 100% for sure. This one's ionic, that one's not. All right, it's probably the most important test that you would run. Right, and we will have little conductivity testers that you can put in the solution that'll tell you on a scale of 0 to 10, okay, how conductive it is. Waxy, nature, crystalline, or waxy. Okay. All right, last thing I probably want to test, and we just talked about it. I use little papers to test it. pH test, yeah, okay. I want to run the pH test last because that's a chemical test. Okay, by putting the pH paper in the solution, I do add some extra ions and stuff that are on the pH paper that allow that reaction to occur. I add that to the solution, and now that solution will be contaminated. I can't run any valid tests after that. So you always want to run pH last, okay? And that will tell me the presence of any strong acids or bases. Okay. When you do this, there'll only be a couple that will have any extreme results. Everything else will be, kind of between like 5 and 8. It'll, be relatively neutral. All right, so back to one other thing here about pH. We said strong acids contain this. All right, so if you get a strong acid, it contains that. A strong base is going to contain this. If I put those two things together, what is that? Water. Okay, that's why water is neutral. Okay. We often can write water as in an ionic way, even though it's a molecular compound. This is essentially what it is: hydrogen hydroxide, okay, and has the most extreme acidic thing and the most extreme basic thing in it. Okay, they kind of cancel each other out, produce something neutral. All right, questions on that properties of compound stuff? Okay, so that's the lesson you're going to come back to when you're doing your lab report, okay, and trying to identify the unknown compounds next week. Okay, this is all information that will be useful to you for that. All right, we got about 15 minutes left, which was kind of my plan here. Okay, I'm going to put some naming stuff on the board that I want you guys to try, and then we'll walk through just again to review some naming stuff. I didn't want to spend the whole class on that, okay, but I still think we need a little bit of time on the naming stuff. So I'm going to put a few things up there for that. Okay, so write the chemical formulas for 1 through 10, and then we'll walk through them. Okay, so as we said, anytime we're either going from name to formula or formula to name, the first step is to determine whether it's ionic or molecular. Okay, lithium bromide contains a metal, lithium, so this is ionic. Okay, so I write the formula for lithium with its charge, +1. I write the formula for bromine with its charge, -1. Those already add up to 0, so I don't need to do anything with it. It's LiBr, and I'm done. Okay, everybody all right with that? Okay, for number 2, I've got beryllium sulfide. Again, beryllium is a metal, so this is an ionic compound. Okay, beryllium has a charge of 2+, sulfur has a charge of 2-. those already add up to 0. So I can just leave it as BES. Okay, I don't go BE2S2. I can reduce that down. Okay, we always reduce if we can. All right, carbon monoxide. Carbon's a nonmetal, oxygen's a nonmetal. There's a prefix in here, so this is what kind of compound? Molecular. Okay, so carbon is C. There's one oxygen, O. That's it. That's what carbon monoxide looks like, CO. Question number 4, we got chromium with a Roman numeral 3 after it, and fluoride. Chromium is a metal. Obviously, we only ever see Roman numerals in ionic compounds. Okay, that little Roman numeral 3 tells me that since chromium has more than one possible charge, I am to use the 3+ charge when I do my drop and swap. Okay, that's what the Roman numeral tells me. Then I have fluorine, which is a -1. So here I drop and swap. The 1 goes to chromium. I don't write it. Okay, the 3 goes to fluorine. I got CrF3 for my formula. All right, and for number 5, I've got phosphorus trichloride, both nonmetals. There's a prefix in there, so it's definitely molecular. Okay, how many phosphorus are there in this compound? Liam, how many phosphorus? 1. Okay, there's no prefix on it. It means 1. Okay, trichloride, that means 3. PCl3. Questions on any of those ones? Okay, I'll give you a couple more minutes and we'll do the next 5. All right, so for number 6, we've got dinitrogen, okay, trisulfide. So it's molecular because it's got prefixes and 2 nonmetals. Okay, di means there's 2 nitrogens, tri means there's 3 sulfides and 2 S3, okay, is what we're looking at there. Number 7, we got diarsenic tetrabromide. Okay, so we got 2 arsenics, which is AS, right? Okay, so we have AS2 tetrabromide. Okay, do I reduce this one? I got a 2 and a 4 there. Right, I don't reduce it. It's molecular. I only reduce ionic compounds. This one specifically said there's 2 of this and 4 of that. That's what I got to go with. Okay, if the prefixes tell me the numbers, then I believe those numbers and I keep those numbers. If I arrive at those numbers by drop and swap and I can reduce them, then I do. Okay, so we reduce ionic, but not molecular in this case. All right, cobalt 2 nitride. So cobalt's a metal. We have a Roman numeral here. So we got cobalt with the 2+ charge. Nitrogen always has a -3 charge, so we drop and swap. We got CO3 and 2. And then for number 9, I've got another molecular compound, nitrogen and iodine together, trinitrogen, so N3, noniodide. How many is that? 9. And again, I don't reduce that because it told me those numbers specifically. Okay, and then for number 10, we got nickel 2 fluoride. So that's a an ionic compound. This is nickel with a 2+ charge. Fluorine has a -1 charge, so I'm going to have NiF2. All right. So again, if that's something you're struggling with, okay, make sure you're using those worksheets and the keys I gave you the other day, and practice those a little bit. If you're still struggling with it, come in and see me for some help next week on that. Now, we still got a couple of minutes, so no, we don't. We don't have any more minutes. It's all done. Okay, have a good weekend, guys, but not too good.